So today we're going to start a foray into the wonderful world of non-interactive proofs. So up until now we've talked about interactive, that's still too thick. Up until now we've talked about interactive proofs, but the problem with interactive proofs is they don't really scale, right? So if I want to run an election protocol, say, and I want to prove that I'm honestly decrypting all of these votes that have been submitted, then I can't really do millions of interactive sessions with every single voter. This is just completely unrealistic. So what the good news is that Sigma protocols especially have a nice way to turn them directly into a non-interactive protocol, so proof. So the idea is that we're going to generate some kind of certificate or signature, you can think of it, that essentially attests to some fact in zero knowledge in a way that you can verify at your own leisure. So the idea is surprisingly simple. Instead of an interactive verifier choosing a challenge, the prover is going to choose a challenge. And then, of course, you ask, if the prover chooses a challenge, well, then can't they just easily cheat, right? Can't they just choose a challenge that they happen to know the answer to? And what we're going to do is we're going to choose the challenge in a fair way. And in a way to be this, what I mean by fair will be determined. And in particular, this means that they won't be able to cheat and use a challenge that they can easily answer. So what we're going to do is we're going to use a hash function to take all of the ingredients of the statement we want to prove. And then because the hash function is in some sense unpredictable, the prover is going to use this hash as a challenge, and they can't really influence the results. They can't change the challenge to one that they like. They're just going to have to live with the challenge. Okay. And the theory is going to get slightly weird because hash functions are slightly weird. So I'm going to start by recalling, air quotes, the definition of a hash function. Or more precisely, the definition of a hash function family. Okay, so a hash function family is a family of functions so parameterized by some lambda, which lives in some space lambda. The details of like how you parameterize the hash functions doesn't really matter. Is where each hash function is. You can sort of model this in a much more general way, of course, but we live in computer science labs, so everything is just bit strings, right? Or everything at least can be represented as bit strings. And one important property of a hash function is that it has a finite codomain, okay? So each hash function is going to take an arbitrarily long bit string and spit out a bit string of length n. And because we're cryptographers, we want to satisfy a few niceness conditions. So in particular, the first is called pre-image resistance. And the idea is that if I sample a random hash function and a random bit string, for Will's benefit, when I use this dollar sign, that means uniformly at random. It's meant to conjure the image of tossing a coin, right? Hence the dollar sign. So we ask that any efficient algorithm cannot find a pre-image, except with low probability. pre-image of D under hash function, except with negligible probability. So we're doing the same thing that we always do here, right? By algorithm, I mean choose your favorite model, but of course we sort of mean Turing machines somehow, right? We sort of mean probabilistic Turing machines in secret. And efficient means polynomial time, and negligible probability means it vanishes faster than the reciprocal of any polynomial. And the second condition, which is not implied, in fact, is not implied, does not imply, these are two genuinely different conditions, is called collision resistance. So this says, if I just choose a hash function uniformly at random, then no efficient algorithm can find two distinct messages, M1 not equal M2, such that they have the same hash. Except with negligible probability. Okay, so the idea is I've got some algorithm that I claim can do pre-image resistance, and you give me a random hash function and a random digest, that's why I use D for digest, then I can't actually find a pre-image except with negligible probability, right? For any fixed choice of hash function and digest, we may allow that you can find a pre-image. In fact, so if you think about it, for a fixed choice of hash function, these conditions are impossible to satisfy, right? If I fix a particular hash function, then of course there is, if I fix a particular hash function and a particular pre-image, then of course there is an efficient algorithm that outputs a pre-image. There are infinitely many pre-images, in fact, so just pick one. Similarly, if you fix a hash function, collision resistance is impossible to satisfy, right? There is at least one collision by the pigeonhole principle, so my algorithm runs in constant time and just outputs a collision, right? So these conditions only really make sense when you talk about hash function families. If I fix a particular hash function, it stops making sense. Any questions so far? Cool. So, for example, we might take our hash function family to be SHA-256, where I prepend my parameter to the message. This is something that we think has these properties. Of course, we can't prove that it has these properties because that would prove P not equal NP. And one of the awkward points theoretically about hash functions, or the ones that are in common use, is we can't even really do reduction, right? We can't even reduce its security to Diffie-Hellman. We just kind of take on faith somehow that this is a collision-resistant hash function family. But what's sort of nice is, even though we can't prove this, it seems to work. And this is, if you ask me, one of the big mysteries in crypto that somehow we don't really understand. Okay, so to sketch before we dive into some more theory, here's how, if we take Schnorr's protocol, the proof of knowledge for a discrete logarithm, a non-interactive version might look something like this. Okay, so the prover is going to first choose a random power. Okay, P is the order of the group, and it's going to commit to G to the power of K. G is a generator of the group. And then it's going to, as its challenge, hash the encoding of the group. So somehow you need to include some description of the group, right? If it's a group of quadratic residues mod P, this is a common choice. If it's a group of quadratic residues mod P, then you would, your description of the group would be the prime number, right? And you also want to include which generator you're using. And you want to include the statement. So remember that what we are proving is that we're proving knowledge of G to the W, of X such that X equals G to the W. Okay, so we include X, which is public knowledge, and we include the commitment, and that makes our challenge. In particular, right, none of these are bit strings a priori, but I hope you believe me when I tell you that you can choose some canonical encoding that everyone agrees on. And then our response is going to be K plus WC mod P, just like in the normal protocol. And then the prover sends to the verifier the commitment and the response, not the challenge. Why does the prover not send the verifier the challenge? Any guesses? No one's brave enough to guess. Just joking. So the reason the prover is not going to bother sending the challenge is because the verifier can compute the challenge, right? The verifier knows all of this stuff, so the verifier is going to compute the challenge itself. G, G, X. The double bars, by the way, just in case, this means a concatenation of bit strings. Okay, and then it's going to check, the verifier is going to check that G to the I equals T X to the C. So this is, as we'll see in a minute, this is a non-interactive protocol. There's no back and forth happening between the prover and the verifier. The prover is just generating something, and the verifier takes that something and does a check on its own. Okay. So one thing that's really important is all of these ingredients that you include here. This is actually crucial. So you can't just include the power. You can't just include the group element X, because otherwise you can have all sorts of problems. So, for example, the prover might prove knowledge for some completely different group, but the verifier can be tricked into thinking that it's checking a proof for the wrong group if it's not in the challenge, right? The fact that it's in the challenge commits the prover to a particular group, a particular generator, a particular value. So you have to include all of the little bits and pieces, otherwise you're going to be in big trouble. And this is a way that things often go hopelessly wrong in the real world. I can link some papers that sort of dive into how proofs break down when you forget bits and pieces in the Discord. Okay, so we kind of understand somehow how this could hope to work, right? Because the prover can't influence the hash function. They have no freedom in this. They can choose their commitment as they like, but that's about as good as they can do. And because the hash function is, in some sense, according to this first board here, the hash function is kind of unpredictable. This means that the prover can only cheat a little bit, right? That's the intuition we're going for. But how do we define soundness and zero knowledge for such things? In particular, our strategy of using special soundness, that extraction procedure, is not really going to work. It's not going to work properly here for two reasons. The first is that the challenge is fixed, so we're in some trouble there. We can't use two different challenges to extract the witness. The second, and this is a bit more subtle, is that the extractor that we defined, and the soundness that we defined using an extractor relies on some notion of rewinding, right? The idea is that it can interact with the prover up to a certain point and then go back and get another interaction with the prover, right? So it runs the prover until it gets a commitment, challenge response, rewinds until before it sent the challenge, sends a different challenge. This is not going to work in the non-interactive case, exactly because there is no interaction happening. So I will try to get to this in the seminar series, but knowledge soundness, which we defined, is a bit more complicated for non-interactive protocols. So we're actually going to today focus on a weaker condition called existential soundness. And this is how we're going to arrive at proving some notion of security for this transformation that I described. Okay. So something we want, the idea of existential soundness or the motivation is that we want to prove properties on encrypted data. Properties of encrypted data. So for example, I might give you two ciphertexts, C1 and C2, and I'm going to prove that they actually encrypt the same message. Okay, so one practical example of this is I might want to prove that in an election context, I'm going to be doing this re-randomization of ciphertexts and shuffling ciphertexts. The idea is that all of the voters post their encrypted votes up on some board, and I'm going to shuffle around all of these encrypted ciphertexts so that when I decrypt them, you can't just say, voter 3 posted vote 3, therefore I know how they voted. I'm going to shuffle them, but I'm going to prove that I didn't change what their vote was, what their message was when I did this. And this comes up a lot in practice, right? These ideas that I'm proving some property of a pair of ciphertexts, of the ciphertext itself, and so on. So this is not knowledge, right? I don't just to prove that some property holds, I don't necessarily need to prove that I know something, right? And we're going to prove that a witness exists, even if I don't necessarily know it. Sidebar, in practice, I do know it, but I don't need the fact that as a verifier, I don't need the fact that the verifier knows the witness. I just need to be convinced that there is one. Okay. So let's define this notion. I'm going to do it for interactive protocols first because I haven't actually defined non-interactive protocols yet. So protocol PV, between the prover and verifier, the interactive one, is existentially sound. For effective relation, which we think of as a subset of X times W, if any prover cannot prove a false statement except with negligible probability. Any prover cheating. If we take some X that does not have a witness, okay, and this is what we mean by false statement. The probability that the verifier accepts is negligible. So this is hopefully a pretty intuitive definition. We're just saying that you can't prove a false statement. You can't prove that something that doesn't have a witness does have a witness, except with negligible probability. And we're going to need this negligible probability escape hatch to do interesting things, as usual in crypto, right? Because we We can't do information theoretic bounds. We're just doing computational bounds. Okay. Questions? Very quiet today, but that's okay. So, in particular, this is a strictly weaker condition than knowledge soundness. Okay. So, with this nice result, if we take some sigma protocol that is special sound with a large challenge space, then it's also existentially sound. So we're going to take our special sound protocol with a large challenge space. So in other words, the reciprocal of the challenge space is negligible. Then it's also existentially sound. So intuitively, if I prove that I know a witness, I also prove that there is a witness. Okay? So it's sufficient to show that there's at most one challenge that the verifier accepts for a false statement. Why is that enough? Because if there were two distinct challenges, then we could use the knowledge extractor to, why is that enough? Because the verifier is choosing among challenges from a large enough space that the chance that they happen to pick the bogus one is negligible. Okay. So it suffices to say that there exists at most one C such that V accepts TCR for some T and R. Okay. Sidebar, let X be a false statement. For X. Okay. So, how are we going to prove this? Well, if there were two distinct challenges that the verifier would accept, then we can use the knowledge extractor to produce a witness, but there is no witness. So if there were two distinct challenges such that the verifier accepts TCR and TC prime, then the extractor gives us a witness. But none exists. Okay.
Question. I mean, a reminder of what the knowledge extractor is. I love the term, but I don't know what it means.
Yeah, so if I have a knowledge sound protocol, special sound is a special case of knowledge sound. If I have a knowledge sound protocol, this means that I have an efficient algorithm where I can interact with the prover in a rewindable way to extract a witness. And in particular, for these three move protocols, like I still have Schnorr's protocol on the second board back there.
Oh, that's convenient.
Yeah. So for special soundness means that you have this three move structure, commit, challenge, response, and it says that if I give you two transcripts, commit, challenge, response transcripts with the same commitment and different challenges, then I can extract a witness. So the knowledge extractor in this case, well, if I can produce two transcripts like this, then the knowledge extractor that we assumed existed by special soundness can produce a witness. Does that make sense?
Yep, that makes sense. All right,
yep.
Thanks.
Okay. But of course, as I say, no witness exists, so I can't do that, so we have a contradiction.
Yeah, it makes sense.
All right. So let's try to see an example. I mean, Schnorr's protocol is somehow not a very interesting thing to use for existential soundness, right? Because of course there exists a discrete logarithm in a cyclic group. This is not interesting, right? So the only reason that Schnorr's protocol makes any sense is exactly because it is a proof of knowledge. So let's look at an example protocol where simply existence is interesting on its own. Okay, so I'm going to demonstrate a proof. Given two group elements and two generators, they have the same discrete logarithm with respect to their generators, okay? So let's take x1, x2 in the group, and g1, g2 generators. And I'm going to prove that they have the same discrete logarithm in zero knowledge. So I prove that x1 equals g1 to the w, and x2 equals g2 to the w for some w. Okay. So how is this going to work? We're essentially just going to do Schnorr's protocol twice in parallel. So prover is going to choose power. Okay, remember I say that P is the order of the group. If the order of the group is not prime, you are in big trouble. So we're always going to assume that. And then my commitment is going to be, well, instead of committing to the power of one generator, I'm going to commit to the power of two generators. Okay, just a pair like this. And I'm going to write this as T1, T2. Okay. Now I'm going to send my commitment off to the verifier. Verifier is going to choose challenge. Send that challenge off. And my response is going to be a single power that works for both of them. And the verifier is going to check both conditions at once. So G1 to the R should be T1, X1 to the C, and G2 to the R should be T2, X2 to the C. Okay. So I claim it's easy to check that this is a special sound sigma protocol. It's really just the same argument as the normal Schnorr's protocol. And that means that this, as a sigma protocol, proves that the prover knows the witness that works, okay? It knows the discrete logarithm that they both share. But in practice, we actually often only care about the fact that such a W exists. Why? I will demonstrate over here. So without lingering too much, I'm going to talk about the Algomal Cryptosystem very quickly. The reason we like Algomal is it's very mathematically simple, so you can sort of do nice toy examples. So the idea is that X is in powers, and Y is G to the X. This is a secret key or private key. This is the public key. And to encrypt a message which lives in the group, we output a pair of values defined to be G to the R n times Y to the R, where R is a blinding factor from the powers. Okay, so this is a nice crypto system because it's automatically randomized, right? If I encrypt the same message many times, I'll get different ciphertexts. It's based on the discrete log it's based on the discrete log assumption. Specifically, the decisional Diffie-Hellman assumption is what you're going to reduce to. But the way that we use this equality of discrete logarithms protocol from before is to prove that something is a legit ciphertext, right? So I want to prove that C1, C2 is legit encryption of M. But I don't want to reveal the power or the secret key. Okay. So how am I going to do this? Easy. I just prove, or P proves. I shouldn't mix pronouns. I guess I said I. So I'm going to use the protocol from the previous board to prove that there exists R such that C1 equals G to the R and C2 equals M times Y to the R, or more accurately, C2 over M equals Y to the R. Okay, so here's an example of a practical zero-knowledge proof where really all we care about is the fact that a witness exists. Of course, in this case, I did actually know the witness, but as a verifier, all you care about is that it's a valid encryption. You're only interested in its validity, which means you only care about the fact that a witness exists. Okay, does that make sense so far? All right, so let's try to define these notions more formally. So I haven't actually said what a non-interactive proof system is supposed to be, so I had better do that. So, non-interactive proof system. It's going to be a pair of algorithms, gen and check. Whoops, I skipped a definition. This is in fact number 3. For an effective relation. It's a pair of efficient algorithms. And the idea is one algorithm generates the proof, the other algorithm generates the proof. Checks the proof. So generate takes an element of the relation, including a statement and a witness, to an element of the proof space. And this one's allowed to be probabilistic. And it's going to map statement witness pairs. W and R to proofs. I in PS, where PS is a proof space of some kind. And the other algorithm is check. Give me statement and proof. And I say accept or reject. And this has to be deterministic. Okay, no probabilistically checkable proofs. Okay. And once again, by algorithms, you can think of it as Turing machines, but I'm deliberately being vague to avoid dealing with Turing machines. So let's define existential soundness for a non-interactive proof system. I only did it so far for an interactive one. I'm going to use NI for non-interactive. It's existentially sound if for all algorithms that map X to the proof space, the probability of a false statement that check accepts is negligible. Efficient probabilistic algorithms. Gen hat take statements to proofs. Note that Gen hat does not necessarily have to take a witness, right? Because it's also trying to generate proofs for false statements. The probability of a false statement that check of gen of x. I wish I had my lasso tool. I made a typo. Gen x set. It's negligible. So this is just a sort of direct port of the statement for interactive proofs. Okay, so I mentioned at the start of today that we can do sort of a transformation, right? Where we produce a challenge out of a hash function. So let's define this transformation properly now. So if we take protocol big pi, which is interactive, a sigma protocol, for the relation R, then the Fiaschemian transformation is, okay, so we're going to say that the transcripts belong to some set. We're going to fix a particular hash function and also some method of encoding and decoding stuff. And then we're going to define a non-interactive proof system. So let transcripts be in T times C times calligraphic R. Because notice that I never actually said what the commitment or responses, what type they are, what set they live in. That's because, you know, you sort of want different answers to that depending on the context. Okay, so we're going to define that to be our set. We fix a hash function.
I'm confused by the fact that the statement here confuses me a bit.
Yes?
So gen goes from R to PS, but gen hat goes from X to PS. I don't really...
Yeah, because gen hat is a cheating generating algorithm. So it's trying to prove false statements. So if we ask for it to always take an element of R, then it's not going to, by definition, it can't prove false statements, right?
Yeah, okay. It just seems like... so you imagine, okay, you give it the input X because, for example, it might be able to exploit some kind of bug or something in order to prove it for X. I guess in my head it was just kind of outputting rubbish or something, but...
Right, yeah, so a concrete example is, I mentioned before that you have to be very careful to hash everything. If you don't do that, you might be able to prove false statements, right? And that's a function of the check algorithm, right? Because the check algorithm is generating the challenge, right? So if the check algorithm generates the wrong challenge, it might accept proofs of false statements.
Okay, cool. I got it.
Okay, so we're going to fix a hash function. And if you're paying close attention, you'll be worried as I say that, but I'm just going to keep talking. And fix an encoding E from X times T to bit strings. And decoding D from finite bit string, from fixed length bit strings to a challenge space. So what we're going to do is we're going to hash a statement and a commitment to form the challenge, hence the encoding, and we're going to take a hash and interpret it as a challenge, hence the decoding. We define a non-interactive proof system with proof space being T times commitments and responses as follows. So gen parameterized by our interactive protocol pi on statement and a witness. It's going to first run prover to get a commitment. Okay, so this is the first step of the Sigma protocol. The prover generates a commitment. And then it's going to set the challenge to be decode hash encode st. Okay, so we are hashing the statement and commitment and then interpreting it as a challenge. That's terrible, that's better. Then we're going to run the prover again on this challenge. So the prover gets X, W, T, C to get response. And then we output TR. Okay, and check. On X pi equals TR. Okay, we're going to also compute the challenge. And then we run the verify algorithm on the transcript. And we write fs pi equals gen pi check. Okay, so that's the Fiaschemian transformation, and this is sort of the first or the older canonical way to take an interactive zero-knowledge proof and turn it into a non-interactive one. And it's doing exactly this procedure that we described before. We take some hash function, use it to produce a challenge, and we call that a day. So, as I said before, we fixed a hash function, and now I said that pre-image and collision resistance don't make sense anymore. The thing is that it seems to work in practice. So, how we do this all the time in applied cryptography, right? We talk about collision resistance, and then we pick a particular hash function, and suddenly it doesn't make any sense, but it still works. So what's going on? There has to be something going on, and there's sort of a standard way to try to make sense of this in theoretical cryptography, which means, unfortunately, more theory and machinery. So I'm going to go ahead and define that now, unless there are any questions about the transformation, just sort of at face value.
I think it's really cool, but I have to admit that I have started to lose you on details. It's not a reason to stop, but it's Yeah, I think I'm getting the big picture. I think this is
Yeah.
a really interesting
Yeah.
trick.
Yeah, the big picture is really, I mean, it's this simple, right? Your challenge is now the hash of your statement and witness, and both parties can compute this independently. So the only thing the verifier needs is your commitment and response in order to check your signal protocol. That's the big picture. And just sort of to write it down in a way that really makes sense, I need to be a bit careful, and that's what all of these notions are for.
Yeah.
Okay, so now we're going to talk about random oracles. This is the mess that is sometimes hidden under the rug. So here's the thing: what property of the hash function did we really care about? We didn't really care about pre-image resistance or collision resistance. What we cared about was heuristically something that satisfies these looks random in some sense, right? It looks random in the sense that given an output, you cannot predict what its input looks like. And given two inputs, you can't predict whether they're going to be equal or not. That's the idea. But it's also deterministic in that if you give it the same thing multiple times, you always get the same answer. So the theoretical cryptography answer to this is the random oracle, okay? And when we introduce the random oracle, we can do suddenly a whole lot of things that we could not do before. That one of the interesting emerging areas in theoretical cryptography is trying to understand exactly what the separation here is. It's still not completely clear. Okay, so a random oracle is very simple. It's a function, looks like a hash function, 0, 1, star, 2, 1, and chosen uniformly at random. That's it. So hash function is a specific hash function family is a family of such functions, and now we just say, okay, well, a random oracle, what it really is I'm choosing some function that spits out digests uniformly at random. You might rightly ask whether such a distribution exists, to which I answer, yeah, maybe. I don't know. Let's just. It's the standard computer science answer is okay. Well, if it doesn't exist, just take the input space to be big enough for everything we care about, and that does the job, right? So it's a uniformly. It's a random function, right? It's just it's a fixed function. So if you evaluate it multiple times, you always get the same answer. But you don't know in advance what answer you're going to get, and you also can't find pre-images, right? Because given some output, if you don't already know what its input is, then it's random from your perspective. To make sense of this, we can also think of a random oracle as stateful somehow. So equivalently, helpful way to think about it is that it's a stateful function where if you query it with something you've already queried, you always get the same answer. But if you give it a new query, it just chooses a value at random. So first we set a map to be the empty set. Stateful function. Where stateful function is not meant to be formally defined. That is a task for another day. So we start with an empty map, and once we get an input B, if there exists, what did I call it? Y such that B lies in the map, we output the Y. Otherwise, we sample a uniformly random Y, and we update the map. And output Y. Okay, so this is meant to capture the essential property of hash functions. Okay, so we're going to pretend the hash function is a random oracle. When we prove security this way, we say that we're working in the random oracle model. So by security, I mean maybe soundness, maybe zero knowledge, whatever security property you want. With this assumption, we say it is secure in the random oracle model. Okay, so intuitively, this gives us a lot more power, right? Because hash functions are decidedly not random. They're not random at all. They just kind of look random. So you cannot prove that a hash function is a random oracle because it isn't. But the heuristic we make here is that a hash function is enough like a random function that if you use a hash function in real life, it will still be secure. I admit that this is really sort of hand wavy, but this is how we are going to proceed. It's really, I mean, we're really just sort of making a strong assumption about the behavior of a real thing just so that we can prove some property, right? Because otherwise we're kind of screwed. Okay, so now I'm going to show you that if I have an existentially sound Sigma protocol, its Fiaschemian transformation is existentially sound in the random oracle model. So in other words, the Fiaschemian transformation works. Okay, so let pi be a Sigma protocol with existential soundness. Then it's Fiaschemian transformation. It's existentially sound in the oracle. Right. Okay, so how am I going to prove this? I'm going to do a reduction. I'm going to show that if I can break existential soundness for the Fiaschemian transformation, then I could break soundness for the original protocol. And I'm going to assume there exists a cheating generator for the Fiaschemian, and I'm going to construct a cheating prover for the original protocol. I'm going to draw some pictures. Okay, so we assume A, which is the gen hat. She's in the Fiaschemian pi. We will construct P, which acts like a P hash for the interactive version. Cheats in pi. By cheat, I mean succeeds, produces a valid proof of a false statement with non-negligible probability, right? Okay, so here's the picture. We think of the random oracle in this stateful mode, right? So what's happening when A runs, it is making some number of queries to the random oracle, right? Maybe zero, but it's certainly making some number of queries to the random oracle. And after a while, it's going to spit out a challenge, a commitment and a response, okay? So without loss of generality, we are going to assume we assume that A at some point int queries C equals R X T. Okay, so what I mean by that is recall that the check algorithm is going to use the challenge that it gets by evaluating the hash function on the statement and commitment, right? H of xt. Right? That's how the transformation was defined. I'm removing the encoding and decoding functions because that's ugly. Now we're replacing the hash function with a random oracle. So we assume without loss of generality that A is at some point going to make this query. Why is it without loss of generality? Because if A doesn't make that query, then at the end of A's procedure, we can just make A do that, right? A is still efficient when it does that, and it doesn't mean that A doesn't succeed. So we can always sort of, we can for free make it an adversary that does eventually do that query. Okay. And here's the trick. Because we think of it as a stateful system, what's going to happen is B is going to act between A and the random oracle, and it's going to replace the challenge that A asked for with the challenge that it got, and by definition, that means that A produces an accepting proof, okay? Because the random oracle is going to give the same challenge to the checker, and because A succeeds, it's going to work, okay? So pictorially, we take our random oracle, and we have A sitting here, and we have the verifier for the interactive protocol sitting here, and B is acting in the middle. Okay, why is B allowed to act in the middle? Because B is going to emulate A. Okay, Turing machines can emulate other Turing machines. So B is going to run an instance, like a copy of A. It's going to emulate a copy of A until A first queries our xt. Right. The first time that A queries this, the random oracle is going to sample the challenge, right? In this stateful setting, the value doesn't exist until A queries it, and then the value magically exists. So at this point, so the picture is that A is interacting with the random oracle via B, and my picture in my notes is slightly incorrect. Okay. So A is going to interact with the random oracle with B intercepting, right? And no, the picture was correct. So B is going to rig the output, right? So this circle indicates that B is going to intercept the output and change it at some point. So when A queries xt, B is going to take this T that A queried and give it as its commitment to V. Okay, so as soon as A queries the random oracle for xt, B is going to take the commitment T that A made and give it to its verifier at the sudden interaction. The verifier does whatever it does and produces a challenge. And the B says, thank you. I am now going to tell A that this is the challenge from the random oracle, so that A does whatever it does with that, and eventually is going to spit out T and R, which B says, thank you for the response. I'm going to use your response. Okay. So a subtlety of this is that B doesn't necessarily know which query A is going to, which query of A is going to be xt, right? Because B doesn't know ahead of time what A's commitment is going to look like, okay? So B doesn't know what T looks like at the point where it intercepts. which is a problem. So B has to guess which query corresponds to xt. Because all B is seeing is a bunch of bit strings. And intercepts that one. Beginning its interaction. With B. Okay, if B guessed correctly, then A, by definition, produces R such that V accepts TCR, right? Because A can fool the check algorithm, which uses the verifier to, which uses the interactive version of the verifier, okay? So by definition, A gets some random challenge that it doesn't know what its structure is from the random oracle, but because A succeeds with non-negligible probability, it can somehow produce a response that works. And then, so B wins, right? If B guessed correctly which query contains the commitment, then B just gives the challenge back, A produces the legit response, and now B has successfully fooled the verifier. But the number of queries A makes is polynomially bounded. Is polybounded. So B still succeeds, or B succeeds 1 over poly. This is terrible notation because I'm running out of time. As often as A, which is non-negligible. That's it, we're done. So this idea of the random oracle appears a lot, and it's going to take a bit of digestion to make sense. Maybe we revisit it next week. Are there any really quick questions? Sorry, Matt.
Not from me. That was cool.
Yeah. Okay. So the upshot is that we can turn interactive protocols interactive zero knowledge proofs into non-interactive ones. Next time we'll do zero knowledge. We'll do the zero knowledge property. So we only talked about soundness so far. The zero knowledge property is sort of similar, but a bit more complex. Okay. Great. Thanks for coming, guys.
Yeah. Thanks, Eleanor.
You can always ping me on Discord as well. See you around.